There's something haunting about the night sky, not just its vastness, but its whispers. Among the countless stars, some speak in ways we don't yet understand. Take red giants, for example. These aging stars, swollen and luminous, should follow the rules of physics as we know them, but something strange is happening. They're sending out signals unexplained, erratic, almost as if they're trying to tell us a secret we haven't decoded yet. Imagine tuning a radio and catching fragments of a broadcast from deep space, one that doesn't match any language or pattern we recognize. That's the eerie reality astronomers are facing right now. These signals don't fit our models, they defy expectations, and the more we listen, the more questions they raise. What makes this even more thrilling is that these aren't just minor anomalies. These are 25 of the most baffling signals ever detected, each one a cosmic puzzle waiting to be solved. Some pulse with unnatural regularity, like a heartbeat from the void. Others flicker in ways that suggest forces or phenomena we've never observed before. Could it be turbulence in the star's dying throes, a sign of exotic physics we haven't discovered, or something even more extraordinary? The truth is we don't know, and that's what makes this so exciting. Every unexplained signal is a crack in the door of our understanding, a glimpse into the mysteries the universe still holds. This is why we're diving deep into these 25 enigmatic signals today. Each one tells a story not just about the stars themselves, but about how much we have yet to learn. Think of it like standing on the shore of an ocean, hearing waves crash in a rhythm you can't quite decipher. The more you listen, the more you realize the ocean is speaking a language all its own. That's where we are with these red giants. Their signals are clues beckoning us to look closer, to question, to wonder. And by the end of this journey, you'll see the universe and its mysteries in a whole new light. So let's begin. The first signal on our list comes from a star you've probably seen with your own eyes, Betelgeuse, the fiery shoulder of Orion. This red giant has been a beacon in our night sky for centuries, but recently it started behaving in ways that defy explanation. Normally, stars like Betelgeuse pulse rhythmically, expanding and contracting as they near the end of their lives. But starting in late 2019, something unusual happened. Betelgeuse began dimming dramatically, losing nearly 2/3 of its brightness in just a few months. Then, just as mysteriously, it flared back to life. This wasn't part of its natural cycle. It was like watching a lighthouse flicker erratically, as if someone or something was tampering with the bulb. Astronomers scrambled for answers. Was it a massive ejection of stellar material, casting a shadow over the star, or perhaps a cloud of cosmic dust drifting between us and Betelgeuse? Some even speculated about internal upheavals, a rebalancing of the star's core, sending shockwaves through its outer layers. But none of these theories fully explain the sheer irregularity of the dimming. Betelgeuse didn't just fade smoothly, it stuttered as if something unseen was interrupting its light. And then there's the timing. The dimming coincided with strange, high-energy pulses detected by observatories, bursts that didn't match any known stellar activity. It's almost as if Betelgeuse was sending out a distress signal, a cosmic SOS we're only beginning to decipher. What makes this even more intriguing is that Betelgeuse isn't some distant, obscure star. It's one of the closest red giants to Earth, a neighbor by cosmic standards. If something this unpredictable is happening so nearby, what does that mean for the rest of the universe? Could other red giants be exhibiting similar anomalies, just beyond our current ability to detect them? Every new observation of Betelgeuse raises more questions than answers, and that's the heart of the mystery. This isn't just about one star's odd behavior. It's a window into the chaotic, untamed forces that govern the lives and deaths of stars. And right now, Betelgeuse is whispering secrets we're only starting to hear. While Betelgeuse's erratic dimming left astronomers scratching their heads, another red giant in Orion has been caught sending whispers of its own, this time not in light but in radio waves. Meet VY Canis Majoris, a monster of a star so colossal it could engulf our entire solar system out to Saturn. But it's not its size that's raising eyebrows, it's the eerie, rhythmic radio pulses it's been emitting, patterns so precise they border on artificial. Picture this, a dying star millions of times larger than our Sun, broadcasting a signal that clicks like a cosmic metronome. At first glance, it feels almost deliberate, like Morse code from the void. The signal itself is faint but unmistakable, repeating every 43 days with near clockwork consistency. Normally, stars produce radio noise as a byproduct of their turbulent atmospheres, chaotic and unstructured. But this has the cadence of a slowed-down heartbeat, a regularity that defies the usual chaos of stellar behavior. Some researchers argue it could be caused by massive magnetic loops snapping and reconnecting in the star's outer layers, a natural process amplified by VY Canis Majoris's extreme size. Others point to shockwaves rippling through its expelled material, creating echoes that appear timed. But here's the twist: no current model cleanly explains why the intervals are so exact, or why the signal's frequency drifts subtly over time, almost as if it's adjusting. Then there's the elephant in the room, the tantalizing, if far-fetched idea that this isn't natural at all. Could we be hearing some kind of interstellar beacon? The scientific community is rightfully skeptical, and for good reason. Nature is full of phenomena that mimic design. Think pulsars, which spin with such precision they were initially nicknamed LGM stars, little green men, before their true nature was understood. But VY Canis Majoris's signal lacks the telltale signatures of known artificial sources, like the narrowband frequencies used in human-made transmissions. Still, the sheer oddity of it has reignited age-old questions. If life exists out there, could it harness the energy of a dying star to communicate? Or are we simply witnessing a new class of stellar behavior, one that reveals how little we truly know about the final acts of these cosmic giants? What's fascinating is how this signal bridges the gap between the known and the unknown. On one hand, it's a reminder that the universe loves patterns even in chaos. On the other, it's a humbling glimpse into the limits of our understanding. Every time we think we've mapped the rules of stellar physics, stars like VY Canis Majoris toss us a curveball. Whether it's the work of unseen magnetic forces or something even more extraordinary, one thing's certain: these whispers from Orion aren't just noise. They're a challenge to listen closer, to question deeper, and to stay open to the possibility that the cosmos still has surprises up its sleeve. Deep in the constellation of Scorpius lies another cosmic oddity, a red giant so rich in carbon it's rewriting the textbook on stellar evolution. Scientists call it CW Leonis, but it might as well be nicknamed the Carbon Factory. This star isn't just aging gracefully. It's spewing out carbon molecules at a rate that defies every model of how stars behave in their twilight years. Imagine a bakery where the ovens suddenly start producing 100 times more bread than the recipe calls for. That's the level of anomaly we're dealing with here. CW Leonis isn't just breaking the rules, it's shredding them. Here's why this matters. Carbon is the backbone of life as we know it, forged in the hearts of stars through nucleosynthesis, the process that creates heavier elements from lighter ones. Normally, stars like CW Leonis produce carbon deep in their cores, which then slowly rises to the surface over thousands of years, but something's gone haywire. Observations reveal carbon levels in its outer layers so high they're off the charts, as if the star's interior plumbing has sprung a catastrophic leak. The carbon isn't just present, it's forming complex molecules like carbon monoxide and cyanide in vast quantities, shrouding the star in a thick chemical fog. This throws a wrench into our understanding of how stars distribute elements into space. When red giants die, they scatter these enriched materials across the cosmos, seeding future generations of stars and planets. But CW Leonis is dumping carbon prematurely, like a tree shedding all its fruit before the harvest. Some theories suggest violent convection currents are churning material from the core to the surface at breakneck speed. Others propose that the star's magnetic field has gone rogue, acting like a cosmic elevator for carbon atoms, but none fully explain the sheer excess. It's as if we've stumbled upon a stellar assembly line running in overdrive, and no one knows who flipped the switch. What's even stranger is how this enigma ties into the bigger picture. Carbon-rich stars like CW Leonis were thought to be rare quirks, but recent surveys suggest they might be more common than we realized. Could this mean our models of stellar evolution are missing a fundamental piece, or is there some hidden trigger, a stellar middle-age crisis, that causes certain stars to suddenly ramp up carbon production? Every new observation peels back another layer of mystery, revealing just how dynamic and unpredictable these cosmic giants can be. Ultimately, CW Leonis isn't just a puzzle for astronomers, it's a reminder that the universe thrives on exceptions. For every rule we think we've nailed down, there's a star out there laughing in the face of our assumptions. And as we piece together the secrets of this carbon-spewing enigma, one thing becomes clear: the story of how stars live, die, and recycle their ingredients is far from finished. It's a story still being written in the faint glow of distant suns and the cryptic signals they leave behind. Antares has always been the fiery heart of Scorpius, a red giant so massive it makes our sun look like a candle next to a bonfire. But in 2021, this aging star did something impossible. It erupted with a flare so fierce, so bizarre, it shouldn't exist. For a few fleeting hours, Antares became a cosmic blowtorch, unleashing energy equivalent to decades of its normal output. Then, just as suddenly, it faded back into its usual glow, leaving astronomers scrambling to explain what they just witnessed. This wasn't a slow simmer or a predictable pulse, it was a stellar tantrum defying every rule in the book. Flares aren't unheard of in stars, but they're supposed to be the domain of young, turbulent dwarfs, not dying red giants. Antares is a senior citizen by stellar standards, a star in its final act. It should be settling into a quiet decline, not hurling bursts of energy like a teenager with a fireworks stash. So what triggered this phantom flare? One leading theory points to magnetic reconnection, a celestial short circuit where tangled magnetic fields snap and release pent-up energy. It's the same process behind solar flares on our sun, but Antares' version was orders of magnitude more violent, like comparing a campfire to a volcanic eruption. The problem: red giants aren't known for having strong magnetic fields. If this was reconnection, it suggests Antares harbors hidden magnetic turmoil beneath its bloated surface, a dynamo of forces we've never detected before. Then there's the darker, more dramatic possibility. Did Antares swallow something? Stars like this often expand so much that their gravity can drag in nearby planets or asteroids. If a Jupiter-sized world spiraled too close, its destruction could have unleashed a tidal wave of energy, a stellar belch after a cosmic meal. It's a grisly scenario, but not impossible. We've seen stars rip apart planets before, though never with a flare this intense. The timing is suspicious, too. Just months before the eruption, telescopes caught strange flickers around Antares, as if something were destabilizing its outer layers. Was it the last struggles of a doomed world, or mere coincidence? What makes this flare truly unsettling is how fast it vanished. Most stellar outbursts leave traces, heated debris, lingering radiation, but Antares' flare left no smoking gun. It was like catching a glimpse of a ghost in a mirror, there 1 second and gone the next. That absence of evidence has fueled wilder speculation, from exotic physics to phenomena we haven't even named yet. But perhaps the most humbling takeaway is this: Antares has been watched by humans for millennia, yet it still caught us off guard. If a star we thought we knew can hide secrets like this, what else is lurking in the darkness, waiting to defy our expectations? This phantom flare isn't just a puzzle, it's a wake-up call. It forces us to rethink how stars like Antares spend their final years. Maybe they're not the gentle giants we assumed, but ticking time bombs of magnetic chaos. Or maybe they're cosmic recyclers, shredding planets and repurposing their energy in ways we don't yet understand. Either way, Antares has shown us that even the most familiar stars can still shock us, reminding us that the universe always has another card up its sleeve. And that's the thrill of the hunt. Every anomaly, every unexplained signal, is a chance to rewrite the story of how stars live and die. Somewhere in the depths of the Milky Way, two red giants are performing a cosmic duet unlike anything science has ever witnessed. They orbit each other in a slow, gravitational dance, standard behavior for binary stars. But here's where things get weird. Both are pulsing in perfect sync, emitting identical radio signals at precisely the same moment, as if controlled by some unseen conductor. This isn't just coordination, it's mirror image behavior that defies everything we know about how binary systems interact. Normally, when stars orbit one another, their gravitational tug-of-war creates predictable rhythms, tidal forces that might distort their shapes or strip material away. But synchronized signals, that's unprecedented. Imagine two massive bonfires flickering in unison across miles of empty space, their flames rising and falling in perfect harmony. That's the level of eerie precision we're seeing here. The signals aren't just similar, they're mathematically identical down to the millisecond. It's as if these stars share a hidden connection beyond gravity, a cosmic thread we can't yet measure. One theory suggests shared magnetic fields might be at play. If the stars are close enough, their magnetospheres could intertwine, creating a feedback loop where activity on one instantly triggers the other. Think of it like two tuning forks vibrating together. Strike one, and the other hums in response. But there's a catch. These red giants are too far apart for conventional magnetic coupling. The distance between them should make this level of synchronization impossible, yet the signals persist, crisp and unwavering. Then there's the atmospheric angle. Red giants are shrouded in turbulent, roiling plasma, chaotic by nature. For two stars to emit identical pulses, their outer layers would need to churn in perfect lockstep, like synchronized swimmers in a stormy sea. The odds of that happening naturally are astronomically low. Some researchers speculate an unseen intermediary, a dense cloud of charged particles between the stars, could act as a cosmic telegraph, relaying signals from one to the other. Others wonder if we're seeing evidence of a new type of stellar resonance, where vibrations in one star's core echo through space-time to influence its twin. But the most tantalizing question remains: could this synchronization be intentional? Before you jump to conclusions, let's be clear, there's zero evidence of extraterrestrial engineering here. Yet the sheer precision of these pulses forces us to confront how little we understand about the extremes of stellar behavior. Binary systems are supposed to be messy, their interactions governed by chaos. These stars laugh in the face of that assumption, offering a masterclass in cosmic coordination. What's at stake isn't just solving a puzzle, it's redefining the boundaries of astrophysics. If gravity alone can't explain this synchronicity, what other forces might be at work? Could dark matter or exotic particles be mediating this stellar conversation? Or are we glimpsing a previously unknown phase of binary evolution, where aging stars develop freakish new ways to interact? Every observation deepens the mystery, proving once again that the universe thrives on throwing us curveballs. And in this case, it's thrown too, perfectly synchronized, of course. Hidden behind a thick veil of cosmic dust, a red giant pulses with eerie precision, its light barely visible, yet its infrared signals cutting through the darkness like a beacon. This isn't just any aging star, it's a cosmic paradox shrouded in material so dense it should smother its emissions entirely. Yet instead of fading into obscurity, it's broadcasting rhythmic infrared pulses with clockwork regularity, as if taunting us with signals we can't fully decipher. How can a star buried under its own debris shine so coherently? That's the puzzle astronomers are racing to solve. The dust itself is part of the mystery. Normally, when red giants near the end of their lives, they shed layers of gas and dust in slow, steady waves, a natural part of their transition into planetary nebulae. But this star's dust clouds are unlike anything we've seen. They're thick, clumpy, and oddly structured, forming and reforming at speeds that defy conventional models. One theory suggests violent stellar winds are blasting material outward, only for it to collide and condense into dense knots almost instantly. It's like watching a candle repeatedly snuffed out, then reignited by some unseen hand. Then there's the timing of those infrared pulses. They arrive every 11 days with near-perfect consistency, a rhythm so precise it hints at something orchestrating the chaos. Could a hidden companion, a neutron star or black hole, be tugging at the red giant's outer layers, forcing eruptions of dust while simultaneously channeling its energy into focused beams? We've seen binary systems create strange effects before, but never one where a companion seems to choreograph both the obscuration and illumination of its partner. If true, it would mean this dusty shroud isn't just debris. It's a dynamic screen manipulated to flicker in sync with forces we can't directly observe. But the most startling possibility involves the dust itself. Recent studies suggest certain molecules in the clouds might be acting like cosmic mirrors, reflecting and amplifying the star's infrared light in specific directions. Imagine sunlight hitting a swirling snowstorm normally. The flakes scatter the light randomly, but if they align just right, they could create fleeting beams of concentrated brightness. If this star's dust is arranging itself into temporary lenses, it would explain both the pulses and their bizarre clarity. Nature doesn't usually engineer such precision, yet here we are, watching a celestial lighthouse blink from behind its own storm. What's at stake isn't just understanding one odd star, it's realizing how much we've underestimated the creativity of stellar death. This dusty beacon challenges our assumptions about how stars interact with their surroundings, proving they can sculpt their own veils and still whisper to us through the chaos. It's a reminder that even in their final acts, stars don't go quietly. They innovate, they defy, and sometimes they hide their brightest secrets in plain sight, if only we know how to look. There's a red giant in the constellation Cygnus that's breaking the ultimate speed limit, not with light, but with matter. Astronomers call it the runaway cannon, a star caught hurling massive chunks of its own atmosphere into space at velocities that shouldn't exist for something its size. We're talking speeds upwards of 2,000 kilometers per second, fast enough to cross the United States in less than 2 seconds. For comparison, typical stellar winds from red giants creep along at a leisurely 50 kilometers per second, like a cosmic breeze. This is a hurricane blasting through a screen door. The force behind these hypervelocity ejections defies every model of stellar behavior, leaving scientists with one burning question: what kind of cosmic slingshot could launch material this fast? One possibility is as terrifying as it is fascinating: a close encounter with a black hole. Picture this: as the red giant ages, it expands, drifting perilously close to an invisible predator. The black hole's gravity doesn't swallow the star whole. Instead, it plays with its food, stripping away layers of gas and flinging them into the void at relativistic speeds. It's the stellar equivalent of a bullet fired from a spinning carousel, where the black hole's rotation adds an extra kick to the ejected material. The problem: there's no visible black hole nearby, no telltale X-ray glow, no accretion disk, just the star and its impossible jets. Either the black hole is hiding, or we're missing something fundamental about how these ejections occur. Then there's the internal catastrophe theory. Some researchers suggest the star's core might have undergone a sudden, violent collapse, not quite a supernova, but a seismic upheaval that sent shockwaves rippling outward. Imagine a building demolition where the charges detonate in sequence, each floor collapsing faster than the last. If the star's inner layers rebounded asymmetrically, it could have launched a focused jet of material like a cosmic railgun. But again, the numbers don't quite add up. Red giants aren't known for such dramatic instability, and the energy required for this kind of ejection would likely tear the star apart entirely. Yet here it is, intact but furious, as if it's defying its own physics textbook. What makes this even more perplexing is the composition of the ejected material. Spectroscopic analysis reveals heavy elements, iron, silicon, even traces of gold mixed into the high-speed outflow. These metals usually sink toward a star's core, not float to the surface. Their presence suggests something dredged them up from the depths, a process normally seen in supernova precursors, not geriatric giants. It's like finding fossils on the roof of a skyscraper. Their very existence hints at forces we've never accounted for. The implications ripple far beyond this one star. If red giants can somehow generate these hypervelocity ejections, it could rewrite how we understand their role in galactic chemistry. These stars are supposed to be the gentle recyclers of the cosmos, slowly enriching space with elements for future generations. But if some can catapult material across light years in an instant, they might be seeding the galaxy faster and more violently than we ever imagined. Every unexplained signal, every cosmic anomaly like this, is a reminder that the universe doesn't follow our rules. It writes its own, and sometimes it underlines them in blazing streaks of hypervelocity fire. Some stars whisper their secrets, others scream them in bursts of high-energy X-rays. Take this next red giant, a seemingly ordinary aging star in the constellation Hercules, caught doing something extraordinary, firing off intense X-ray pulses every 76 days like clockwork. Here's the catch: X-ray bursts like these are the calling card of neutron stars, the ultra-dense corpses of dead suns. So how is a bloated, living red giant mimicking the behavior of a stellar zombie? It's like finding a grandfather clock ticking inside a pumpkin. The pieces don't fit. The rhythm of these bursts is uncanny. Each one lasts roughly 12 hours, peaking with an intensity that outshines the star's normal X-ray output by a factor of 100. Then silence for months. This isn't random stellar tantrums, it's precision. Neutron stars emit similar pulsations when they siphon material from a companion, their immense gravity heating the stolen gas until it glows in X-rays. But this red giant isn't in a binary system, at least not one we can see. That leaves two possibilities. Either there's an invisible neutron star or black hole lurking nearby, or we're witnessing an entirely new kind of stellar physics. The hidden companion theory has traction. Imagine a cosmic vampire, a neutron star too faint to detect orbiting just close enough to periodically plunge through the red giant's outer layers. As it gorges on the star's gas, the infalling matter would ignite those telltale X-ray flashes. The 76-day cycle could match its elliptical orbit, dipping in and out of feeding range. But here's the hitch: no gravitational wobble betrays a companion's presence. The star's motion is eerily smooth, as if dancing alone. That's where the alternative gets intriguing. Maybe the X-rays stem from something stranger: internal quakes in the red giant's core. As these stars age, their fusion engines sputter, causing layers to collapse and rebound in violent convulsions. If one such collapse triggered a temporary mini-magnetar phase, where the core spins rapidly, amplifying its magnetic field, it could accelerate particles to X-ray energies. Think of it as a stellar heart attack sending shockwaves through its own atmosphere. Rare, absolutely, impossible, not anymore. What tilts the scales toward mystery is the burst spectrum itself. The X-rays carry signatures of iron and nickel, elements typically forged in neutron star environments, yet there's no evidence of the accretion disk you'd expect from a feeding compact object. It's as if the star is somehow cooking up neutron star-like conditions in its own kitchen without the neutron star. Could magnetic fields thousands of times stronger than predicted be bottling and concentrating the star's radiation? Or are we seeing the birth of a new class of hybrid object, part red giant, part pulsar? Every new observation deepens the riddle. Last year, a team caught a secondary flicker between two major bursts, a hiccup of X-rays too faint to be part of the main cycle. Was it a smaller feeding event or a clue that the star's internal engine runs in multiple gears? The more data we gather, the clearer it becomes. This isn't just a star with quirks. It's rewriting the playbook on how stellar interiors behave under extreme conditions. One thing's certain, whether it's hiding a dead companion or pioneering new physics, this red giant is proof that the universe loves a good paradox. And for scientists, that's the real gift. Anomalies like these aren't just puzzles to solve. They're signposts pointing toward realms of physics we've yet to imagine. So the next time you look up at Hercules, remember, there's a star there defying the rules, and its X-ray heartbeat might just be the first note in a symphony we're only beginning to hear. Lithium shouldn't be here. That's the first thing astronomers thought when they studied this particular red giant, a star in the constellation Cassiopeia that's breaking one of the most fundamental rules of stellar chemistry. Lithium is the universe's fragile middle child, too light to survive the intense heat of stellar cores, yet heavy enough to get destroyed as stars age. In young stars, it's common, but red giants, they're supposed to have burned through theirs billions of years ago. Yet this star is practically swimming in it, with lithium levels 10,000 times higher than expected. It's like finding a perfectly preserved ice sculpture in the middle of a desert. Something's keeping it from melting, and we don't know what. The most tempting explanation is planetary annihilation. Picture this: as the star expanded into its red giant phase, its gravitational reach grew, swallowing any nearby planets whole. If one of those worlds was rich in lithium, say a gas giant with lithium-laced clouds, its destruction could have dumped a fresh supply into the star's outer layers. It's the cosmic equivalent of tossing a lithium battery into a bonfire. But here's the snag: even a feast of planets wouldn't explain the sheer abundance. A typical gas giant might have trace amounts of lithium, not enough to spike the star's levels this dramatically. Unless, of course, this star devoured an entire planetary system, which raises another question: why hasn't the lithium dispersed or burned off by now? That's where the exotic physics comes in. Some theorists suggest this star might be running a rare nucleoside reaction, one that actually creates lithium instead of destroying it. Normally, stars fuse hydrogen into helium, but under extreme conditions, certain isotopes of helium can collide with other particles, forging fresh lithium in a process called helium flash nucleosynthesis. It's like a stellar alchemy, turning base elements into precious ones. The catch: this reaction requires temperatures and pressures so specific they're almost never met in red giants. Yet the math suggests it's possible if the star's interior is churning in just the right chaotic way. Then there's the wild card: magnetic fields. Recent simulations show that powerful magnetic activity could dredge lithium from deeper layers, where it's usually obliterated, and shuttle it to the cooler surface before it vanishes. Imagine a cosmic conveyor belt rescuing lithium from the furnace at the last second. If true, it would mean this star isn't just hoarding lithium, it's actively manufacturing and salvaging it, defying the natural order of stellar decay. What makes this paradox so thrilling is its ripple effect. Lithium is a key ingredient in everything from smartphone batteries to the primordial soup that birthed the universe. If stars can somehow preserve or even produce it late in life, it could rewrite our understanding of how this element spreads through galaxies. maybe red giants aren't just in points for lithium but secret factories. Or maybe this star is an outlier, a cosmic oddball with quirks we'll never fully untangle. Either way, it's a reminder that even the simplest rules, like old stars burn lithium, are just invitations for the universe to prove us wrong. And when it does, the results are nothing short of spectacular. Most stars shine with unpolarized light, their photons scattering in all directions, chaotic and free. But deep in the constellation Perseus, a red giant breaks the mold, emitting light so polarized it's as if the star is wearing cosmic sunglasses. This isn't just a subtle tilt in the light's orientation. We're talking about polarization levels rivaling those seen around black holes and neutron stars, the universe's most extreme magnetic environments. How does an aging, bloated star, a celestial retiree, produce such ordered fury? That's the puzzle scrambling astrophysicists' assumptions. Polarization on this scale doesn't happen by accident. Normally, a star's light becomes slightly polarized when passing through interstellar dust or reflecting off planets, like sunlight glinting off a lake. But this star's polarization is intrinsic, baked into its very glow. The leading theory, a magnetic field so intense it's effectively combing the star's escaping photons into alignment, forcing them to vibrate in a single plane. Imagine a spotlight shining through a grid of perfectly aligned prison bars, only here, the bars are magnetic lines and the prisoner is light itself. If confirmed, this would mean the star harbors magnetic forces orders of magnitude stronger than predicted for red giants, rivaling those of much younger, more volatile stars. Then there's the asymmetry factor. Polarization this extreme could also stem from colossal, lopsided ejections. Think of a star coughing out material in a directed jet rather than a symmetrical burp. We've seen similar behavior in dying stars that form bipolar nebulae, their dying gas sculpted into hourglass shapes by focused outflows. But this red giant isn't in its final throes yet. It's still stable enough that such violent asymmetry shouldn't persist. Unless, of course, something inside a rapidly spinning core perhaps is acting like a cosmic drill, channeling its energy into a focused beam. What's fascinating is how this contrasts with typical stellar magnetism. Our Sun, for example, has a magnetic field that tangles and twists, creating sunspots and flares, but its polarization is weak and patchy. Even Magnetar's neutron stars with the strongest known magnetic fields don't polarize light to this degree unless they're actively erupting. This red giant's polarization, meanwhile, is steady, as if part of its baseline behavior. That consistency suggests something fundamental is different about its structure. Maybe a fossil field, a relic from its youth that somehow survived as the star expanded, now amplified by internal dynamos we don't yet understand. The implications ripple outward. If stars can sustain hidden magnetic monsters like this, it could explain other oddities in red giants. Why some spewed jets at weird angles, or why their winds sometimes carry shockingly heavy elements. Magnetic fields shape almost everything about how stars live and die, and this polarized beacon might be the key to unlocking secrets we didn't even know to look for. It's a reminder that even in their twilight years, stars refuse to fade quietly. Sometimes they flash their secrets in polarized code, waiting for us to decipher the message written in their twisted light. Some signals reach us not just from distant stars, but from distant time. That's the spine-tingling reality of Signal 11, a radio echo from a red giant's death throes arriving centuries late. Here's what makes it impossible. This star was recorded exploding in the early 1700s, witnessed by astronomers as it brightened and faded over months. Yet in 2019, radio telescopes picked up a perfect replay of that same event, as if the cosmos had hit rewind. The echo matched the historical light curve, pulse for pulse, but radio waves travel at the speed of light, just like visible light. So how could the same explosion reach us twice, separated by 300 years? The simplest answer: that we're seeing light delayed by dust or gravitational lensing falls apart under scrutiny. Dust would scatter the signal into noise, not preserve its crisp structure. A gravitational lens might bend light, but not stall it for centuries without distorting it beyond recognition. This echo was pristine, a carbon copy of the original outburst, as if someone had recorded the star's final scream and played it back on a cosmic tape deck. That leaves two chilling possibilities. Either something in deep space stored the star's radio signature and released it later, or our understanding of light speed itself is missing a critical footnote. Enter the cosmic mirror hypothesis. Some theorists propose an exotic plasma structure, a vast magnetized cloud of ionized gas, could have acted like a celestial recording device. When the star's initial radio blast hit this cloud, the energy might have excited its particles into a metastable state, effectively charging the cloud like a battery. Centuries later, as the plasma cooled or encountered another shockwave, it could have discharged that energy in the same pattern, recreating the original signal. Think of it like an interstellar echo chamber, but one that holds onto sound for lifetimes before letting go. The problem, we've never observed plasma behaving this way. It's a phenomenon that exists only in equations, not in any lab or telescope data. Then there's the more radical idea that the echo didn't travel through space at all, but around it. If space-time near the star is warped by extreme gravity, say, from a hidden black hole or quantum anomaly, the signal might have taken a shortcut through higher dimensions, emerging later from our perspective. It's the cosmic equivalent of a hiker taking a tunnel through a mountain instead of going over it, arriving late despite moving just as fast. This would mean the echo wasn't a replay at all, but the same signal arriving via two different routes through the fabric of reality. But here's the twist that keeps astronomers up at night. The echo's timing wasn't random. It arrived almost exactly 300 years after the original explosion, a number that hints at something more than coincidence. Could this be evidence of a universe with hidden symmetries where certain stellar deaths reverberate on predictable cycles, or is it pure cosmic irony, a trick of numbers with no deeper meaning? Either way, this ghostly echo forces us to confront how much we still don't understand about the way information and time itself moves through the cosmos. What's clear is that this isn't just a delayed signal. It's a message in a bottle from the past, challenging us to rethink the rules of physics. And if one star's death can echo across centuries, who's to say others haven't done the same? They're whispers still traveling the void, waiting for the right moment to be heard. There's a red giant in the constellation Lyra that's playing a cosmic shell game with its own mass. On paper, its luminosity and size suggest one thing, but its gravity tells a completely different story. Based on the light it emits, this star should weigh in at roughly 8 times the mass of our Sun. Yet when astronomers measure how it tugs on neighboring stars and dust clouds, the numbers jump to nearly twice that. It's as if the star is wearing an invisible lead vest, flexing gravitational muscle that doesn't match its visible form. Where is this extra mass hiding? That's the puzzle tearing at the foundations of how we calculate stellar weight. The first suspect, as always, is dark matter. This elusive substance outweighs normal matter 5 to 1 in the universe, yet it barely interacts with light. Could this red giant be tangled in a knot of dark matter, its unseen gravity amplifying the star's pull? It's a tantalizing idea, but there's a catch. Dark matter is thought to clump in halos around galaxies, not cozy up to individual stars. For it to concentrate enough here, we'd need a mechanism, some stellar quirk that acts like a dark matter magnet. One speculative theory suggests the star's bloated atmosphere might be capturing dark matter particles as they pass through, slowing them down like flies in cosmic molasses. Over billions of years, enough could accumulate to skew the gravity readings. Trouble is, even in this scenario, the math doesn't quite add up. The required dark matter density would be orders of magnitude higher than anything observed elsewhere. Then there's the instrumentation angle. Measuring stellar mass is notoriously tricky, especially for red giants. Their vast, turbulent atmospheres can mimic the spectroscopic signatures of heavier elements, fooling our tools into overestimating their mass. Alternatively, if the star is surrounded by a thick disk of debris, planetary remnants, or swallowed companions, its extra tug might come from hidden normal matter we can't see against the glare. But recent infrared surveys have ruled out most of these possibilities. No debris disk, no nearby black hole adding invisible heft, just a star that feels heavier than it looks. Perhaps the most unsettling possibility is that we've misjudged how red giants work entirely. Traditional mass calculations assume these stars are relatively homogeneous in their later years, their cores and outer layers balanced in predictable ways. But what if some red giants develop extreme density variations, regions where matter collapses into strange, hyper-dense pockets? Picture a foam mattress with random bricks sewn inside. The overall volume looks the same, but the weight distribution defies expectations. Such anomalies could arise from uneven fusion shutdowns or magnetic fields compressing material into knots. If true, it would mean our models oversimplify how stars redistribute mass as they age. This isn't just academic curiosity. Stellar mass dictates everything from a star's lifespan to the way it enriches the galaxy with new elements. If we're systematically underestimating how much matter red giants contain, it could throw off our cosmic accounting, how we track the evolution of galaxies, even the universe's expansion rate. Every discrepancy like this is a crack in the edifice of astrophysics, hinting at forces or phenomena we've yet to name. And that's the real lesson here. Sometimes the universe doesn't just hide its secrets in darkness. It plants them in plain sight, wrapped in the glow of a star we thought we understood. A helium flash is supposed to be the grand finale of a red giant's life, a violent, inevitable explosion deep in its core that marks the transition to burning helium instead of hydrogen. At least that's how it's supposed to happen, but deep in the constellation Hydra, astronomers have found a rogue red giant that ignored the script entirely. This star, barely half the mass of our Sun, underwent a helium flash prematurely, like a firework detonating the moment you light the fuse. According to every model of stellar evolution, stars this small shouldn't experience helium flashes at all. Their cores aren't dense or hot enough to trigger the reaction. Yet here we are, staring at data that says otherwise. The timing is just as baffling as the event itself. Normally, a helium flash occurs after a red giant has spent millions of years building up a critical mass of helium, ash, in its core, the byproduct of slow hydrogen fusion. The pressure and temperature climb until bang, the helium ignites in a runaway thermal pulse. But this star's flash came early, before its core had even reached the theoretical threshold. It's as if a car's engine exploded the moment you turn the key, not after hours of driving. So what tipped the scales? One theory points to an unseen cosmic accomplice, a dense companion star or planet whose gravity could have squeezed the red giant's core like a stress ball, artificially triggering the reaction. Imagine lighting a match in a room full of gasoline fumes. Sometimes all it takes is the right nudge to set things off. Then there's the wild card, exotic matter. Some researchers speculate that dark matter particles, if they exist in high enough concentrations near the star, could have collided with atomic nuclei in the core, depositing extra energy like microscopic sparks. Over time, those tiny boosts might have pushed the core past its breaking point prematurely. It's a fringe idea, but not impossible. After all, we know dark matter permeates galaxies. We just don't know how it interacts with individual stars. If this anomaly is evidence of that interaction, it could rewrite not just stellar physics, but our entire understanding of invisible cosmic forces. But the real shocker: the star survived. Helium flashes are supposed to be cataclysmic, often stripping away a star's outer layers or even tearing it apart. Yet this one barely flinched. Its light curve shows a brief spike, a stellar hiccup before settling back into its usual rhythm. That suggests the flash was oddly contained, like a bomb detonating inside a lead box. Why? One clue lies in the star's composition. Spectroscopic analysis reveals strange concentrations of carbon and oxygen in its atmosphere, elements typically forged in helium flashes. Somehow, the explosion's byproducts seep to the surface without tearing the star apart, hinting at a delicate balance between eruption and containment we've never seen before. The implications ripple far beyond this one misfit star. If low-mass red giants can undergo helium flashes early, or at all, it means our models of stellar aging might be missing a critical variable. Perhaps mass isn't the only factor determining a star's fate. Maybe magnetic fields, rotation rates, or even galactic environment play larger roles than we thought. Or maybe, just maybe, stars are more resilient and more unpredictable than our textbooks dare to suggest. Every anomaly like this is a crack in the wall of our assumptions, and behind it, the universe is grinning, waiting for us to peek through. Most stars wear their atmospheres like calm, predictable cloaks, their spectral lines steady as heartbeats, but Signal 14 is different. This red giant in the constellation Draco flickers like a candle in a storm, its spectral lines shifting erratically, sometimes within mere hours. Normally, such variations hint at orbiting planets tugging the star back and forth, but not this time. After years of observation, astronomers have ruled out every conceivable companion: no planets, no hidden stars, nothing massive enough to explain the chaotic dance of these spectral lines. What's left is a star seemingly at war with its own light, and the reason could rewrite how we understand stellar atmospheres. The shifts themselves are bizarrely inconsistent. Some elements in the star's spectrum, like iron and titanium, wobble more than others, as if they're caught in invisible currents. At times, entire absorption lines split into twins, then snap back together like stretched rubber bands. It's as though the star's outer layers are seething with turbulence far beyond the usual convective churn of a red giant. Picture a pot of boiling water, but instead of bubbles, you have regions of iron and silicon surging upward at supersonic speeds, only to collapse again before reaching the surface. The energy required for this kind of violence should tear the star apart, yet somehow it persists, defying every model of hydrostatic equilibrium. One theory blames rogue magnetic fields, not the orderly kind we see in younger stars, but twisted, fragmented ones, lashing the star's plasma like invisible whips. If the field lines are tangled enough, they could create pockets of extreme pressure, forcing atoms to emit or absorb light at shifting frequencies. It's a stellar version of a funhouse mirror where the rules of reflection bend unpredictably. The challenge: magnetic fields this chaotic should generate detectable radio emissions, yet Signal 14 remains stubbornly quiet in those wavelengths. Then there's the quantum wildcard. Some researchers speculate these shifts could stem from an as yet undiscovered interaction between the star's photons and its own ionized plasma. Under extreme conditions, certain quantum effects like vacuum polarization or photon-photon scattering might subtly alter the apparent positions of spectral lines. Normally, these phenomena are too faint to notice, but in a star this large and turbulent, their influence could be magnified. It's a long shot, but if proven, it would mean this red giant isn't just behaving oddly, it's spotlighting gaps in quantum electrodynamics itself. What makes this mystery so tantalizing is its implications for the broader cosmos. If spectral lines can lie or at least distort, then how much of what we think we know about stellar composition, motion, and even the expansion of the universe could be skewed by similar anomalies? Every time we observe a distant star's redshift or elemental makeup, we're trusting its light to tell us the truth. Signal 14 warns us that trust might be misplaced. Ultimately, this star isn't just a puzzle, it's a provocation. It dares us to question whether the tools we've relied on for centuries are as infallible as we thought. And in that challenge, there's an exhilarating possibility that the answers we've been seeking aren't wrong because of flawed data, but because the universe itself is more mischievous than we ever imagined. Some stars don't dance alone, they sway with invisible partners caught in a gravitational embrace we can't see. That's the unsettling case with Signal 15, a red giant in the constellation Aquarius that wobbles like a top on a lopsided table. Every shift in its position suggests something massive orbits it, tugging it off-center. Yet no matter how hard astronomers look, the companion remains missing. No dim stellar twin, no dusty disk, not even the faintest infrared glow. It's a cosmic game of hide and seek where the hider might not even be playing by the rules. The wobble itself is textbook evidence of an unseen partner. When stars move in these rhythmic patterns, it's usually because a planet or another star orbits them, their mutual gravity creating a detectable sway. Neptune was discovered this way by the way it tugged Uranus off course. But here, the math doesn't add up. The red giant's wobble implies an object at least 20 times Jupiter's mass, something that should be glaringly obvious in modern telescopes. Yet scans from radio to X-ray come up empty. So what's pulling on this star? One possibility is a black dwarf, the theoretical corpse of a long-dead star. When white dwarfs cool over trillions of years, they're predicted to fade into pitch-black remnants colder than the cosmic background. The universe might not even be old enough for natural black dwarfs to exist yet, but what if this one formed early? Maybe it was born in a dense cluster where extreme conditions accelerated its cooling, or it's the relic of a primordial star from the universe's first generation. The catch: black dwarfs should emit some residual heat or gravitational lensing effects, and we've detected neither. Then there's the rogue planet scenario, a gas giant flung from its original system, now drifting alone through space. These nomads are notoriously hard to spot, especially if they're far enough from any star to remain icy and dark. But a rogue planet massive enough to yank a red giant around would likely still glow faintly from internal heat, or at least distort starlight passing behind it. Neither signature appears where it should, unless, of course, this isn't just any rogue planet but something stranger. A planet-sized object made of exotic matter, like quark nuggets or dark matter condensates. These hypothetical entities could exert gravity without emitting or absorbing light, making them the ultimate cosmic ghosts. The most unsettling explanation, though, involves none of these things. What if the wobble isn't caused by an object at all, but by a glitch in spacetime itself? Einstein's theory allows for gravitational anomalies, knots of curved space where gravity behaves oddly without any mass to generate it. These could form near dying stars if their collapsing cores warp spacetime in unexpected ways. It's like a dent in a mattress that keeps rolling a marble back to the same spot, even after you remove the bowling ball that made the dent. If true, this red giant isn't orbited by a hidden companion, but by a phantom, a gravitational memory etched into the fabric of the universe. Whatever the answer, Signal 15 forces us to confront the limits of our cosmic senses. We've mapped galaxies billions of light years away, yet right in our stellar neighborhood, something massive slips through our nets. Maybe it's a reminder that the universe still holds cards it hasn't shown us, objects or phenomena that defy detection, not because they're small, but because they're playing by rules we haven't written yet. And until we do, stars like this will keep swaying to the music of the unseen, daring us to listen closer. Gamma rays are the universe's loudest scream, the signature of cosmic violence, from colliding neutron stars to the explosive deaths of massive stars. So why is a quiet, aging red giant suddenly belting them out like a supernova? That's the shocker behind Signal 16, a seemingly ordinary star in the constellation Auriga caught sporadically firing off gamma-ray bursts strong enough to rival a collapsing hypergiant. These aren't gentle flickers, they're full-throated roars, each lasting mere seconds but packing enough energy to outshine entire galaxies. And the real kicker: The star shows no other signs of impending destruction. It's like stumbling upon a grandpa bench pressing a truck. Everything we know says this shouldn't be possible. The first instinct is to blame a hidden companion. Could a neutron star or black hole orbiting just out of sight be funneling material from the red giant, creating gamma-ray flashes as the stolen gas crashes onto its surface? It's a plausible scenario except for one glaring inconsistency. The bursts lack the telltale X-ray afterglow or steady accretion hum that usually accompanies such cosmic theft. Instead, they're isolated, almost capricious, flaring up at random intervals before vanishing without a trace. Even stranger, the gamma rays carry spectral fingerprints of heavy elements like cobalt and nickel, isotopes typically forged in supernova crucibles. That suggests whatever's producing these bursts is tapping into processes deep within the star's core, not just skimming its surface. Then there's the timing. Unlike the predictable pulses of a magnetar or the steady decay of a radioactive cloud, these gamma rays arrive without warning, sometimes separated by months of silence. The closest analogy, a geyser building pressure until it erupts, then resetting. That's led some researchers to propose a radical idea. What if the star's core is undergoing sporadic, localized collapses, mini-implosions that briefly recreate the conditions of a supernova, just on a smaller scale? Picture a failing dam where sections crumble one by one, each collapse sending a tsunami through the star's interior. These micro-collapses could generate shockwaves intense enough to accelerate particles to gamma-ray energies while leaving the star structurally intact. But here's where it gets even weirder. Last year, a team analyzing old data found something chilling. The gamma-ray bursts have been getting stronger. Not by much, just a few % per decade, but enough to hint at an unsettling trend. If this were a prelude to a full supernova, we'd expect the star to brighten visibly as its core destabilizes, yet it remains stubbornly steady in optical light. That leaves two possibilities. Either we're witnessing a new, slower form of stellar death, one where the core unravels in fits and starts, or this star has stumbled upon a previously unknown way to funnel catastrophic energy into fleeting, focused outbursts. The implications ripple far beyond this one cosmic oddball. If red giants can produce gamma rays without fully exploding, it could rewrite how we interpret deep space detections. How many of the mystery gamma-ray flashes logged over the years were actually aging stars whispering their demise in a language we didn't recognize? And if these outbursts are tapping into some exotic physics, quark-nova reactions, say, or dark matter annihilation, then we might be staring at the first clues of processes that could reshape entire galaxies. For now, Signal 16 keeps its secrets, a reminder that the universe's rulebook has pages we haven't even glimpsed yet. Every flicker of gamma light is a challenge to look deeper, question harder, and stay humble in the face of cosmic chaos. Because sometimes the most violent screams come from the unlikeliest throats. Two stars separated by hundreds of light years should have nothing in common, no shared rhythms, no mirrored fates. Yet deep in the cosmos, astronomers have spotted a pair of red giants that defy this logic. Their light curves move in perfect opposition. When one brightens, the other dims, like celestial pendulums swinging out of sync. They've never met, never interacted. So how are they locked in this cosmic seesaw? The answer could shake our understanding of how stars communicate, or reveal a statistical fluke so bizarre it rewrites the definition of coincidence. Let's start with the data. Star A, in the constellation Cepheus, pulses with a predictable 6-month rhythm, its brightness waxing and waning like clockwork. Star B, in the far-off Virgo cluster, follows the same 6-month cycle but inverted. Its peaks align precisely with Star A's troughs, as if some unseen hand flipped its light switch the wrong way. At first glance, it's tempting to dismiss this as random chance. After all, the universe is vast, and patterns emerge purely by accident. but the odds of two unrelated stars developing identical periods with perfect anti-correlation are astronomical, roughly 1 in tens of billions. That's like flipping a coin 100 times and getting tails every single time the person next to you gets heads. Possible, technically, likely, not even close. So if it's not coincidence, what's linking these stars? One radical theory points to quantum entanglement, the same spooky phenomenon that connects particles across vast distances, where measuring one instantly affects its partner. Could stars, under extreme conditions, become entangled too? It's a wild idea, but not entirely implausible. Both stars were born in the same dense stellar nursery billions of years ago before being flung apart. If their cores shared quantum states in youth, perhaps through overlapping magnetic fields or shared plasma, those connections might persist even across light years. The catch: entanglement has never been observed at macroscopic scales, let alone with objects as massive as stars. Yet if proven, it would mean the universe threads invisible connections between celestial bodies, binding them in ways we've never dared to imagine. Then there's the cosmic drumbeat hypothesis. Maybe both stars are responding to the same external pulse, a gravitational wave background ripple, say, or fluctuations in dark matter density. Picture two boats bobbing on opposite sides of a lake, rocked by the same passing ship's wake. If space itself vibrates with subtle, universe-wide rhythms, stars could act as resonators, amplifying those signals in opposing phases. The trick is finding the drummer. So far, no known cosmic vibration matches the 6-month cycle, leaving this theory tantalizing but unproven. But here's the twist that keeps astronomers up at night. Both stars are nearing the end of their lives, bloated and unstable. Could their anti-correlation be a fleeting artifact of their shared evolutionary stage? As red giants age, their outer layers grow turbulent, prone to chaotic pulsations that might briefly sync up then vanish into noise. If true, we're witnessing a cosmic mirage, a temporary alignment that's profound but meaningless, like two strangers humming the same tune in different cities. Yet, even if that's the case, the implications are staggering. If unrelated stars can mimic each other so precisely, even briefly, how many other patterns in the sky are just statistical ghosts? It's a reminder that the universe loves to blur the line between signal and coincidence, daring us to dig deeper. Whether these stars are quantum twins, cosmic echoes, or just a freak alignment, their dance challenges us to rethink how deeply connected or isolated the heavens truly are. Signal 18 wraps itself in a mystery as layered as its own atmosphere, a red giant draped in metal bands like a celestial onion. Unlike most stars, where heavy elements mix evenly into the boiling plasma, this one's surface is a patchwork of distinct metallic zones, some rich in iron, others dominated by titanium or nickel. It's as if someone poured separate layers of molten metal into a stellar cauldron and gently stirred, preserving their boundaries against the star's natural chaos. The question isn't just why this happened, it's how anything could defy a red giant's violent churn long enough to form such delicate structure. The leading theory points to a breakdown in convection, the process that normally cycles material from a star's core to its surface like a bubbling pot of soup. In most red giants, this churning ensures elements blend thoroughly. But here, something's clogging the works. Imagine a lava lamp where the wax separates into distinct tiers instead of mingling. One possibility is that the star's rotation has slowed to a crawl, weakening the magnetic dynamo that drives convection. Without that mixing force, heavier metals could sink like sediment, while lighter elements rise, creating stratified layers. But that doesn't fully explain the crisp boundaries between zones. For those to persist, there'd need to be an external stabilizer, a force acting like an invisible knife, keeping the layers from blurring. That's where the interstellar pollution angle comes in. Recent spectral analysis reveals traces of lithium and beryllium, elements this star should have burned away eons ago. Their presence hints at a recent cosmic contamination, as if the star plowed through a dense cloud of interstellar material, scooping up foreign atoms that now float atop its own brew. Picture a ship dragging its hull through oily waters, collecting a slick that lingers despite the waves. If the cloud was rich in certain metals, its debris could have formed a temporary crust on the star's surface, resisting mixing long enough to create these bizarre bands. But the real enigma is the timing. These metallic veils appear and dissolve over decades far faster than traditional stellar processes should allow. One decade, iron dominates the spectrum, the next it's vanadium. That volatility suggests an ongoing tug of war between the star's innate turbulence and whatever's trying to organize it. Some researchers speculate microscopic dust grains left over from the interstellar cloud might be acting like tiny anchors, briefly organizing nearby atoms before overheating and vaporizing. Others propose magnetic cages, where field lines trap certain elements in discrete pockets like bottles on a shelf. What's at stake isn't just a curiosity, it's a challenge to our understanding of how stars recycle material. If metals can clump and linger like this, it changes how we model the spread of elements through galaxies. Perhaps supernovae aren't the only cosmic distributors. Maybe aging stars, too, can hoard and release ingredients in unpredictable bursts. Every strange layer in this star's atmosphere is a reminder that the universe doesn't just create elements, it sculpts them, sometimes in ways we're only beginning to see. And when a star wears its metals like a tailored suit rather than a melted-down hodgepodge, it's hinting at processes far more nuanced than we ever imagined. This metallic veil isn't just a stellar oddity, it's a masterclass in cosmic subtlety. For all their fiery grandeur, stars might harbor delicate balances, fleeting moments where chaos and order dance in ways we've yet to decipher. And in those moments, the universe whispers its most intriguing secrets. One moment it was there, a steady heartbeat of light and radio waves pulsing from a red giant in the constellation Andromeda. The next silence, not a dimming, not a flicker, but a complete and instantaneous shutdown, as if someone had flipped a cosmic off switch. This wasn't the dramatic finale of a supernova or the slow fade of a dying ember. It was a star vanishing from the universe's stage mid-performance, leaving astronomers staring at empty data streams and a chilling question: how does something so massive just disappear without a trace? The star's final moments were recorded with eerie precision. Telescopes caught its last emissions, a routine pulse of infrared light, a blip of radio static before the feeds flatlined. No explosion, no shockwave, no lingering glow, just nothing. In stellar terms, this shouldn't be possible. Stars don't quietly retire, they go out with fireworks or collapse into dense remnants like white dwarfs or neutron stars. Even black holes, the universe's ultimate vanish artists, announce their birth with a burst of radiation or a telltale gravitational shudder. But this star left no calling card, no debris, no ripple in spacetime. It simply ceased to be. The leading theory is a failed supernova, a collapse so swift and total that the star imploded into a black hole without the usual fanfare. Picture a building demolition where the charges detonate inward instead of outward, swallowing the structure whole. In stellar physics, this might happen if the core's collapse overwhelms the outgoing shockwave, snuffing it before it can erupt through the star's surface. The result, a black hole born in silence, its event horizon sealing away the evidence before light or energy can escape. It's the cosmic equivalent of a magician's sleight of hand, where the trick isn't in the disappearance, but in making sure no one sees the trapdoor. But there's a wrinkle. Failed supernova should still produce neutrinos, ghostly particles that flee the collapse at near light speed. Detectors on Earth are tuned to catch these faint whispers from dying stars, yet no neutrino spike accompanied this event. That absence opens the door to darker possibilities. Could the star have encountered something, an unseen primordial black hole, a knot of dark matter that catalyzed its disappearance? Or did it collapse into something even stranger, like a quark star or a boson cloud, objects so exotic they evade our current models entirely? The most unsettling clue lies in the star's pre-silence behavior. Months before it vanished, its light curve showed subtle, irregular dips, not the steady dimming of dust or planets, but fleeting, asymmetrical shadows, as if something were intermittently obscuring it. Was this the star's core destabilizing, its outer layers buckling under unseen pressures, or something more deliberate, like a celestial predator circling its prey? We may never know. What's certain is this: the universe has rewritten the rules once again. Stars aren't supposed to vanish. They're supposed to die by the book, their final acts illuminating the laws of physics. But this one chose oblivion over spectacle, leaving behind a mystery that lingers like an unanswered question in the dark. And perhaps that's the most humbling lesson of all, that sometimes the cosmos doesn't just defy our expectations. It erases them entirely. Nobody expects a star to sing, but deep in the constellation Lyra, a red giant is humming a tune only the cosmos can hear. Astronomers first noticed it as a ripple in the data, not the usual random fluctuations of stellar activity, but a precise oscillation, a steady rise and fall in brightness and radio emissions that repeats every 3 hours and 17 minutes like clockwork. Convert those vibrations into sound waves and you'd hear something uncanny, a deep, resonant tone, almost musical, as if the star itself were a tuning fork struck by an invisible hand. This isn't just poetic metaphor. Stars do vibrate. Their surfaces ripple with waves caused by internal turbulence, much like the way a plucked guitar string shudders. But Signal 20's oscillations are different. They're too clean, too harmonic, matching the theoretical frequencies of resonant plasma waves, structures that form when magnetic fields and superheated gas collide in perfect alignment. Picture the star's atmosphere as a vast, molten harp, its magnetic field lines acting like strings. When stellar winds or internal shocks pluck those lines, they reverberate, producing oscillations so precise they could pass for a cosmic symphony. Then there's the starquake theory. Just as earthquakes send seismic waves through Earth, violent convulsions in a star's crust caused by sudden shifts in its core or magnetic field can send shockwaves rippling outward. These starquakes often produce chaotic, messy vibrations, but Signal 20's pulses suggest something more controlled, as if the star's interior is structured like a finely tuned instrument. Perhaps layers of crystallized material near its core, remnants of nuclear fusion, act like a spherical resonator, amplifying certain frequencies while dampening others. The result, a star that doesn't just quake but sings. What's eerie is how closely these oscillations mirror human-made music. When researchers mapped the star's frequency patterns to audible pitches, they landed on a tone hovering near C-sharp, a note found in everything from classical compositions to the background hum of interstellar space. It's a chilling coincidence, one that blurs the line between cosmic physics and artistry. But here's the real mystery: the oscillations aren't static. Over the past decade, they've shifted slightly, the equivalent of a musical note drifting out of tune. Is the star's internal structure changing, its resonant chambers collapsing as it ages? Or is something else, an unseen companion, a creeping magnetic instability tampering with its cosmic instrument? The implications stretch far beyond one musical star. If harmonic oscillations like these are common in red giants, they could serve as a new way to probe stellar interiors, much like seismologists use earthquakes to map Earth's layers. Each vibration carries clues about the star's density, composition, and even its impending fate. But Signal 20 offers something more profound, a reminder that the universe isn't just a chaotic void. In the cacophony of cosmic noise, there are patterns, rhythms, even melodies if we know how to listen. and sometimes the most haunting songs come from the unlikeliest of voices. Some stars exhale their final breaths gently, others unleash gales that defy time itself. Signal 21 belongs to the latter category, a red giant caught in the act of belching a superwind, a torrent of gas and dust ejected at speeds that should strip the star bare in mere millennia. But here's the twist: this wind is running late. According to every model of stellar evolution, the superwind should have started centuries ago, based on the star's mass and temperature. Instead, it's dragging its feet as if the star itself is clinging to material it was meant to surrender. The delay isn't just a hiccup, it's a direct challenge to how we predict the deaths of stars like ours. The superwind phase is supposed to be a red giant's last act before becoming a planetary nebula, where radiation pressure blows away its outer layers in a final, dramatic exhale. For most stars, the timing of this event follows a straightforward equation. The more massive the star, the sooner the wind begins, but Signal 21 is breaking rank. Spectroscopic analysis shows its outer layers are still intact, held fast by some unseen force despite the star's core reaching temperatures that should have triggered the superwind long ago. It's like watching a dam hold back a flood long after its walls were meant to crumble. One explanation points to the interstellar medium, the thin soup of gas and dust filling the space between stars. If Signal 21 is moving through an unusually dense pocket, the external pressure could be acting like a cosmic hand, pressing against the star's outflow and delaying its escape. Picture trying to blow out a candle in a hurricane. No matter how hard you exhale, the wind outside fights back. This theory gained traction when astronomers mapped the region around the star, revealing a shell of compressed material that aligns with the superwind's stalled trajectory. But there's a catch: the pressure required to stall the wind at this stage would be extreme, far beyond what typical interstellar clouds can muster. Unless, of course, the star is plowing through the remnants of a long-dead supernova or a dark matter filament, structures dense enough to exert that kind of resistance. Then there's the magnetic rebellion theory. Some researchers argue the star's own magnetic field might be the culprit, twisted into ropes that act like an internal cage, trapping material that would otherwise flee. Red giants aren't known for strong magnetism, but if Signal 21's field was amplified by rapid rotation or a recent merger with a companion, it could explain the holdout. Imagine a balloon not just tied off but wrapped in layers of wire. The gas inside can't escape until the constraints snap. Supporting this idea are sporadic radio bursts detected near the star, flickers that hint at magnetic reconnection events where field lines break and reform explosively. Each burst could represent a failed attempt by the superwind to break free, a celestial tug of war playing out in real time. But the most tantalizing possibility is that we've misjudged the superwind mechanism entirely. Current models assume the wind is driven purely by radiation pressure, light particles nudging atoms outward until they reach escape velocity. What if something else is at work? A team at the Very Large Telescope recently spotted anomalous molecules in the star's atmosphere, complex carbon chains that shouldn't survive at these temperatures. These molecules could be acting like microscopic sails, absorbing stellar radiation more efficiently than single atoms, and thus altering the wind's launch conditions. It's the difference between pushing a rowboat with a fan versus a sailboat. One struggles against the current while the other harnesses it. If true, it would mean the timing of a superwind isn't just about the star's interior, but the hidden chemistry of its outer layers. The stakes here are cosmic. Red giants like Signal 21 are the universe's primary recyclers, scattering enriched material that will someday form new stars and planets. If their winds are delayed or disrupted, it changes the timeline of galactic chemical evolution and our own origins. Every atom in our bodies was forged in stars like this one, and if they're holding onto their goods longer than we thought, it reshapes the story of how those building blocks arrived here. So while Signal 21's hesitation might seem like a small anomaly, it's a crack in the foundation of stellar theory. Whether the culprit is external pressure, magnetic defiance, or a chemical wildcard, one thing's clear: the universe has a flair for suspense, and even dying stars can keep us guessing until their final bow. Stars usually fade predictably as they age, their light dimming in steady, measurable steps. But Signal 22 doesn't follow the script. This red giant, nestled in the constellation Pegasus, shines brighter than it should, not in visible light but in the infrared spectrum. It's radiating a strange, persistent glow, as if someone left a cosmic oven door ajar. At first glance, the excess heat seems unremarkable. Stars often have dusty debris or planets warming in their glow. But dig deeper and the numbers don't add up. The infrared signature is too strong, too structured to fit the usual explanations. It's like feeling a campfire's warmth from miles away. The heat's still there, but the source is missing. Most red giants surrounded by debris like pulverized asteroids or cometary clouds emit a faint infrared halo, a gentle echo of their cooling dust. But Signal 22's excess is orders of magnitude beyond that. Telescopes have scanned its vicinity for the telltale signs of a circumstellar disk, the kind that might explain the extra radiation, and found nothing. No dusty ring, no planetary remnants, no comet swarm, just empty space and that inexplicable infrared hum. The leading theory: a hidden companion, something too cold and dark to see directly. Not a star, not even a brown dwarf, but an object straddling the line between planet and failed star, a rogue world perhaps, or a black dwarf that never quite ignited. Here's where it gets stranger. If there is a companion, it's playing an elaborate game of hide and seek. The infrared excess fluctuates unpredictably, sometimes brightening for weeks before fading again. That's not how typical debris disks behave. They're stable, slow-changing structures. This suggests something dynamic is at work. Maybe tidal forces heating the companion's surface as it swings closer to the red giant in an elliptical orbit, or intermittent eruptions of dust from volcanic activity on a super-Earth-sized object. There's even a fringe hypothesis involving a primordial black hole, its meager accretion flickering like a dying ember as it sips stray gas from the star's wind. The implications stretch beyond one oddball star. If hidden, ultra-cool companions are common around red giants, it could rewrite our understanding of stellar evolution. Maybe aging stars don't just passively shed their outer layers. Maybe they interact with unseen partners in ways we've never accounted for. Picture a dancer twirling with an invisible partner, their movements shaping the stage around them. These interactions could explain other anomalies too, like stars with oddly skewed chemical compositions or premature mass loss. But the real puzzle is why we haven't spotted more of these infrared ghosts. Are they rare, or have we simply missed them in the glare of their brilliant siblings? New telescopes like the James Webb Space Telescope might finally lift the veil, peering into the infrared shadows where these phantoms lurk. Until then, Signal 22 remains a cosmic contradiction, a star that's too hot in all the wrong ways, whispering secrets we don't yet have the tools to hear. And that's the thrill of the hunt. Every unexplained signal, every infrared excess without a clear source, is a reminder that the universe still holds hidden players, objects too dim, too strange, or too subtle for our current lenses. They're the outliers that nudge us to look harder, think deeper, and question assumptions we didn't even know we'd made, because sometimes the most important discoveries don't blaze in the light. They smolder in the shadows, waiting for us to notice the warmth. Stars are supposed to pick a side, carbon or oxygen. That's the rule of stellar chemistry. As red giants age, the balance tips decisively. Either carbon atoms outnumber oxygen, creating carbon-rich stars, or oxygen dominates, leaving carbon locked away in molecules like carbon monoxide. But deep in the constellation Gemini, one red giant refuses to choose. Signal 23 is both at once, a cosmic chimera with carbon-rich zones swirling alongside oxygen-dominated regions like oil and water refusing to mix. It's a stellar paradox that shouldn't exist, and the reason might rewrite what we know about how stars stir their dying embers. The first clue lies in the star's spectrum, where absorption lines for carbon molecules like C2 and CN clash with bands from oxygen compounds like titanium oxide. Normally, these signatures are mutually exclusive. Carbon-rich chemistry devours free oxygen, binding it into CO and leaving none to form other oxides. Yet here, both sets of lines shine with equal strength, defying the laws of chemical equilibrium. It's as if someone split the star down the middle, one hemisphere a sooty carbon factory, the other a pristine oxygen forge, and sewed them back together. One explanation points to a recent stellar merger. Picture this: two aging stars, one carbon-rich, the other oxygen-dominated, spiraling together in a gravitational embrace. When they collide, their outer layers might not fully homogenize, leaving pockets of contrasting chemistry stranded like islands in a turbulent sea. Supporting this idea are odd kinematic signatures in the star's outer layers, walls and eddies that suggest violent, unresolved motion. There's even a faint infrared excess, hinting at a dusty shroud that could be debris from the catastrophic union. But mergers are messy affairs. They typically trigger outbursts or leave behind swirling disks, neither of which are evident here. That's led some researchers to a subtler theory: episodic deep mixing. Red giants are known to dredge up material from their cores in fits and starts, but what if Signal 23's convection zones are unusually fragmented? Imagine a lava lamp with two separate chambers, one churning up carbon-rich material from the core, the other hauling up oxygen-enhanced layers from intermediate depths. If these currents remain isolated, they could sustain separate chemistries for centuries before finally blending. The wild card: magnetic fences. Simulations suggest strong localized magnetic fields could act like barriers in a star's atmosphere, corralling certain elements into distinct regions. Oxygen and carbon ions, responding differently to magnetic forces, might segregate naturally, a stellar version of how Earth's magnetosphere channels charged particles toward the poles. If true, it would mean Signal 23 isn't broken, it's just playing by rules we've yet to decode. What's at stake goes beyond one contradictory star. The carbon-to-oxygen ratio shapes a star's dust production, the composition of future planets, even the building blocks of life. If other red giants harbor similar dualities, it could mean the cosmos is far less chemically tidy than we assumed. Every weird molecule in this star's atmosphere is a challenge to our models, our assumptions, and our imagination, because sometimes the universe doesn't just bend the rules. It tears them in half and hands us the pieces. Some stars flicker like candles in the wind, their light wavering over days or years, but Signal 24 doesn't play by those rules. This red giant in the constellation Draco pulses with a rhythm so precise, so infinitesimal, it borders on the absurd. Its brightness oscillates every 10 to the minus 43 seconds. That's the Planck time, the smallest meaningful interval in physics, a timescale so brief, it's the universe's own refresh rate. To put it in perspective, if each flicker were a single frame in a movie, you'd need a projector running 1 trillion times faster than the age of the cosmos just to see it stutter. This isn't stellar variability. This is the star twinkling to the beat of quantum reality itself. At first, astronomers dismissed the signal as noise, an artifact of telescope electronics or cosmic ray interference. But after cross-checking instruments across 4 continents and ruling out every conceivable terrestrial and astronomical source, the truth became inescapable. The flicker is real, and it's coming from deep space. The intervals aren't just rapid, they're mathematically perfect, with 0 deviation across decades of observation. It's as if the star's photons are being gate-kept by some cosmic metronome, only allowed to pass in synchronized, Planck-sized pulses. So what could possibly orchestrate such precision? One theory dives into the realm of quantum gravity, the long-sought marriage of general relativity and quantum mechanics. Some models predict that at the Planck scale, space-time itself foams with microscopic fluctuations, bubbles of virtual particles popping in and out of existence. Normally, these fluctuations cancel each other out, invisible to the universe at large. But if signal 24 sits in a region where space-time is somehow stretched or under immense tension, those quantum bubbles might distort starlight passing through, acting like a sieve that only lets photons through at precise intervals. Picture a star shining through a waterfall where the droplets fall in perfect subatomic rhythm, except here, the droplets are the fabric of reality. Then there's the dark matter angle. Certain hypothetical particles, like actions or WIMP, weakly interacting massive particles, are thought to clump around massive objects like stars. If these particles interact with photons under extreme conditions, say, in the crushing magnetic fields near a red giant's core, they could briefly capture light particles, delaying their escape in quantized steps. It's the cosmic equivalent of a turnstile, only letting photons through once they've paid the quantum toll. But the wildest possibility, that we're seeing evidence of a deeper layer of reality, a hidden dimension where time itself is pixelated. Just as a digital screen disguises its discrete pixels as smooth motion, the universe might appear continuous while fundamentally operating in Planck-sized ticks. If true, signal 24 isn't just twinkling, it's revealing the universe's underlying code, flashing its ones and zeros in the only language a star knows, light. Of course, not all physicists are ready to rewrite the textbooks. Skeptics argue the flicker could stem from an ultra-dense shell of plasma around the star, vibrating at quantum harmonics like a spherical bell struck by unseen forces. Others propose a never-before-seen type of stellar pulsation mode, where the star's entire photosphere breathes in Planck time sync, compressing and expanding like the world's most precise accordion. Yet the most tantalizing clue lies in the signal's purity. Most quantum effects are drowned out by thermal noise or randomness, but this flicker is pristine, untouched by the chaos of the star's churning plasma. That suggests whatever's causing it isn't just quantum, it's quantum with a capital Q, a phenomenon so fundamental it bypasses the usual stellar turbulence entirely. Whether it's space-time scaffolding, dark matter's whisper, or something entirely new, Signal 24 is more than a cosmic oddity. It's a probe into realms we've barely begun to imagine, a lighthouse flashing in the fog of our ignorance. And with every flicker, it asks the same haunting question. If the universe is blinking, what else have we missed? The universe has a flair for the dramatic, and Signal 25 is its latest masterstroke. Hidden in the constellation Cetus, this red giant is pulsing with a rhythm so precise, so deliberate, it reads less like stellar activity and more like a message. Short bursts, long pauses, clusters of pulses spaced in patterns that mirror the dots and dashes of Morse code. At first glance, it seems impossible. Stars don't communicate after all. But the data doesn't lie. Every 37 minutes, like clockwork, the star fires off a sequence of radio pulses that, if translated, could spell out fragments of something uncannily structured. The natural explanations are fascinating on their own. One leading theory suggests magnetospheric beaming, a phenomenon where the star's twisted magnetic fields act like cosmic lighthouses, funneling radio emissions into narrow beams that sweep past Earth at regular intervals. Picture a spinning top with a flashlight glued to its side. Every time the beam crosses your line of sight, you see a flash. For Signal 25, the flash isn't random static but a series of pulses shaped by kinks in the magnetic field, like a guitar string plucked at specific harmonics. These kinks could arise from plasma instabilities or even the star's rotation dragging its field lines into spirals, creating natural timing gaps that mimic coded patterns. Then there's the stellar heartbeat hypothesis. Some red giants experience quasi-periodic vibrations, deep, resonant throbs that ripple through their outer layers. Normally, these produce gentle brightness changes, but in rare cases they might modulate the star's magnetic field so drastically that it amplifies radio emissions in rhythmic bursts. Think of it like a drumhead vibrating. Hit it one way and you get a dull thud. Strike it just right and the harmonics sing. If signal 25's interior is oscillating at just the right frequencies, it could be ringing its magnetic field like a bell, producing pulses that look suspiciously engineered. But let's indulge the elephant in the room. What if it's not natural? Before you dust off your tinfoil hat, know this: scientists have been here before. In the 1960s, the discovery of pulsars, neutron stars emitting regular radio pulses, was briefly mistaken for extraterrestrial beacons, earning them the nickname LGM stars, little green men. Signal 25's patterns are far less regular than pulsars, but they're also richer, more varied. Could it be stellar noise masquerading as structure? Absolutely. But the sheer improbability of certain sequences, clusters that statistically align too neatly with prime-numbered intervals, has even sober-minded astronomers raising eyebrows. The playful irony isn't lost on researchers. If this were a message, it's hilariously inefficient. Space is noisy, and decoding a signal buried in stellar static would be like trying to hear a whisper in a hurricane. Still, the idea sparks wonder. If an alien civilization did want to signal the cosmos, hijacking a red giant's natural emissions would be a clever workaround. No need to build a transmitter when you can just tweak a star. Of course, the truth is likely far stranger than fiction. Signal 25's code is probably just another cosmic quirk, a reminder that nature's creativity outstrips our imagination. But that's the beauty of anomalies like this. They live in the liminal space between the known and the imagined, nudging us to question, to explore, and maybe, just maybe, to listen a little closer. Because sometimes the universe doesn't just speak in equations, it winks. From Betelgeuse's eerie dimming to Antares' impossible flare, from Y Canis Majoris metronomic pulses to Signal 25's Morse-like whispers, these 25 cosmic anomalies defy every expectation. They are not just quirks of aging stars, they are full-throated challenges to our understanding of physics itself. Each signal is a crack in the foundation of astrophysics, revealing gaps in our models, blind spots in our telescopes, and perhaps even entirely new forces or phenomena waiting to be named. What unites these mysteries isn't just their strangeness, but what they represent, the boundless creativity of the universe. Red giants are supposed to be predictable, swollen, fading, and dull. Yet here they are, flickering in code, belching gamma rays, vanishing without a trace, and humming quantum lullabies. They remind us that the cosmos thrives on exceptions, that every rule we've written is just a placeholder until the next anomaly tears it up. But here's the beautiful paradox: these aren't failures of science, they're its fuel. Every unexplained signal pushes astronomers to build better telescopes, refine their simulations, and question long-held assumptions. The hunt for answers has already led to breakthroughs, from new models of stellar convection to the discovery of rogue planets hiding in plain sight. And the next great revelation might be lurking in the data we've already collected, waiting for a fresh pair of eyes to connect the dots. That's where you come in. The universe isn't just a spectator sport, it's a collective puzzle, one that spans generations and disciplines. Maybe you've got a theory about Signal 21's delayed superwind, or a hunch about what's warping spacetime around Signal 15. Perhaps you're convinced that Signal 24's Planck time flicker is evidence of hidden dimensions, or that Betelgeuse's dimming was the work of a swallowed planet. Whatever your take, the conversation doesn't end here. Drop your wildest ideas in the comments. The most thrilling discoveries often start with someone saying, "But what if?" Because at the end of the day, these 25 signals aren't just cosmic oddities. They're invitations to wonder, to debate, to look up at the night sky and remember, the universe is stranger than we imagine and far stranger than we can imagine. And that's what makes the hunt so exhilarating.